Okay, in this video we're going to look at factoring using the distributive property. And so at this point in my particular Algebra 1 class, what we've done so far with our polynomials is that we have added them, subtracted them, and multiplied them together. And so if you kind of follow that through to what you think the next thing that you would learn would be, the next thing is division. And that is kind of what we're going to be talking about now. Whenever we think about dividing polynomials, though, it's also important for us to go back and kind of understand the different ways we can divide numbers. So for instance, we do this thing with numbers and we start doing it in maybe pre-algebra or even a class or two before pre-algebra where we look at the factors of a number. The factors of a number are pairs of numbers that multiply to get that. There's different ways of writing this, but as a foreshadowing technique, I suppose, the way I want to write this is just, what are two numbers that multiply together to get 24? So I like to do this systematically. I always start with 1 and the number, and then if it's divisible by 2, that'll come next, and then I just have to figure out, okay, 2 times what is 24? And then I'll keep going with 3 and 8 and 4 and 6. If I asked you to factor 24, we'd have these 4 pairs of numbers. So the idea, though, is that we're talking about what multiplies to get what we started with. And that's going to be important for us in today's lesson to understand that that's what the word factor means. 13 only has one set of factors, 1 and 13. And we call this a prime number because of that. And in some ways, we almost don't really even count it as being factorable because the only factors are this set of factors that's maybe not as interesting, which is just 1 and the number. Then with 38, we have 1 and 38, and then we have 2 and 19. And that's it. There's nothing else that works. One of the ways that we can check to make sure those are the only factors is when we get to 2 and 19 and we see that those are both prime, that means there can't be anything else that works. If either of them was something divisible by something else, there would have to be at least one more set of factors. Kind of like over here when we did 2 and 12, 2 is prime, but 12 is not, so there had to be more factors than just the ones we listed so far. Another important concept or idea to this whole dividing polynomials thing is a number is blank by another number if that number divides evenly with no remainder. The word we're looking for here is divisible. So saying that you can divide a number by another number, something else, but this idea that we sometimes care about dividing evenly, that a number can be divisible by another number when it divides evenly, that is going to be something that's important for us as we go forward. That yes, we can do 21 divided by 2. We are capable of dividing these numbers, but that does not mean that 2 is divisible into 21. Okay, so that is an important distinction that we'll look at. I'm going to skip this last part. It was a look at long division, but I don't think we really need to do it right now, so let's just go past it. Eventually, we are going to learn how to divide polynomials using long division. It may not happen for you in Algebra 1, or if it does happen in Algebra 1, just keep in mind that you'll do it again in Algebra 2, and it'll be much more important to really understand it in Algebra 2. That's kind of where we expect for there to be a certain level of mastery is in Algebra 2 versus Algebra 1. But for now, we're just going to focus on how do we split a polynomial up into its factors, kind of like how did we split 24 up into its factors, into two things that multiplied to get what we started with. So the first way that we're going to learn to factor a polynomial is by looking for the greatest common factor of all the terms. And this is something you had to do in pre-algebra most likely, where you looked at different things, and it could have just been numbers, it could have been numbers and letters, and we decided what the greatest common factor would be. And then today, what we'll do is we'll take that a step further and we will factor out the greatest common factor. And what we should end up with is the opposite of what we do with the distributive property. So you'll see what I mean by that after we do example 1. So on example 1, we've got two terms here, making this a binomial. And what we want to do is we want to look at these two terms and see what they have in common that we can divide by. So if I look at the numbers 2 and 4, and I think about it, what number can I divide into both of those evenly? and that would be 2. Not only is it that we want a number that divides into them both, we want the biggest number possible. So this had been 4 and 8. We'd pick 4 instead of 2. Since it's 2 and 4, we want to pick 2. We'll always be able to divide 1 into what we have, but that is not really what we're going for. We want the biggest number possible, so that would be a 2. We're going to write that down because that's going to be part of our answer. We also look at our x's. If they both had an x in common, then that would also be part of our greatest common factor, and we would write it down and take it out. There's not an x in both of them, so that's not going to happen on this one. Once we have our greatest common factor, what we're doing is dividing both terms by that greatest common factor. And so we could call this like factoring out the 2. If I factor the 2 out of 2x squared, well, those cancel and it leaves me with just the x squared. If I factor out the 2 from the 4, I divide those and I am left with 2. So this is my answer. What this should look like is what we did in our last video at the beginning, where we used the distributive property. And so we don't want to go back and distribute this because then we'll end up with what we started. It asked us to factor. We now have 2 things that multiply together to get what we started with. So we've factored this out, which is what we wanted to do. So it's kind of weird at first that this is what we're trying to do, but it is. We're trying to split it up into 2 things that multiply together to get what we started with. So let's look at some more examples. This time we've got 4 terms. Now, when we find the greatest common factor here, it has to go into all 4 of them. So that's going to make this a little tricky. Because if I look at the numbers, 4 and 8 are divisible by 4, but 6 isn't divisible by 4, 9 is not divisible by 4, and 6 is divisible by 2, but 9 is not divisible by 2. And these up here aren't divisible by 3 like these are. There isn't actually a number that I can divide all of these by. So I could write down 1 if I wanted to, but typically we don't write down 1 because it's understood to be there. So I can write down 1 or not. Then I would look at these letters. If I've got n to the 5th, n to the 4th, n cubed, and n squared, the greatest common factor of these variables is an n squared. Because inside of each of these, n to the 5th has an n squared. N to the 4th has an n squared. N cubed has an n squared. And most importantly, the smallest one, n squared, has an n squared. So we could, if we picked just n to take out, well, they'd still all have an n after we took it out. Or if I tried to pick n cubed, well, this last one doesn't have that many n's, so that wouldn't work. So we want to pick basically the smallest exponent, whichever one that is, that's what we're going to take out. And we're going to do like we did in the last one, and it's like we are dividing these all by n squared. And so when we do that, this is where we use our exponent skills to say, well, one's on top and one's on bottom, so I subtract my exponents. The numbers will remain whatever they are because I'm not dividing by a number. So this will be 4n cubed minus 8n squared. Remember, I'm subtracting my exponents. Minus 6n to the first, which we don't need to write the 1. And then plus 9. If we subtract these exponents, we get 0. Into the 0 is just 1. Or we can say, okay, those cancel out because they're the exact same. And they leave us with the 9 that's in front. This is our answer on this problem. Okay, so I don't remember how many examples there are, but this should just be pretty much more of the same for the most part. It shouldn't be anything too super different. On this one, actually, there is a small difference because when I look at this and say what's in common, they have a number in common, which is 5. They have y's in common, which is y squared, but they also have a negative in common. And so we're going to take out that negative as well because all 3 of them have it. Definitely, if all of your terms are negative, you should take out a negative. And then there's some times where taking out a negative would be beneficial even if they're not all negatives. And it usually has to do with our first term. If our first term is negative, it's very rarely wrong to take out a negative. We don't always have to take out the negative, but very rarely would we say, oh no, you shouldn't have done that. Because if the first thing's negative, it actually might help us to take that negative out. later on whenever we get to more complicated problems. So I'm going to divide each of these by negative 5y squared. If it helps you to write this out, you definitely should. If you can just think it in your head, then that would be fine. The negatives cancel out on each. We need to divide the numbers and subtract the exponents. So that's 2y to the 4th plus 5y squared plus 4 without any y's because those are the same and cancel each other out. And this would be our answer. On each of these, by the way, we could check our answer at the end by using the distributive property to see if we get what we started with. So on a quiz or a test where the stakes of getting it right are high, that would be a good way of checking your answer. Oh no, on example 4, we've got more than one letter. So we're going to look at this as basically 3 different problems. We're going to look at the numbers 3, 6, 15, and 96, which are all divisible by 3. Then we're going to look at just the m's and say, what is the most m's, or sorry, what is the least m's that I have? I've got an m squared, an m squared, and an m, so I can only take out an m. I'm going to look at the n's and do the same thing. All of them have at least an n, but no higher, so I'm going to take out an n, and then I'm going to divide each of these by 3mn. And I'm going to try really hard not to accidentally write all m's or all n's because that is not helpful. So on this first one, we divide by the 3, and it cancels and gives us 1. We subtract our exponents for the m and get just m. We subtract our exponents for the n and get just n. We divide here and get negative 2. The m's cancel, but then I have n squared. Here I've got plus 5. I'm left with an m, and the n's canceled. Oh, 96 divided by 3, that would be 32. The m's cancel, and I'm left with an n, and that would be my answer. If you're curious if we would be able to combine any of these, either at the beginning or at the end, as like terms, whenever you have more than one variable, they have to look the exact same. So we would have to have something like 3mn plus 7mn. Those add together. Or if we had m squared and n for both of them, that would be fine. But if we end up with something where like the m is squared in one and the n is squared in the other, those aren't like terms, so we can't add them together. So that's why none of these could be combined. That's why that wasn't a step in this process. So that is factoring out the greatest common factor using the distributive property.